Hi, my name is Dr. Ellen McGlade McCullough, and it is my privilege to welcome you to our Science National Honor Society Induction 2020 virtual edition. Tonight we will be inducting the juniors to the Science National Honor Society. The executive committee will be taking care of the ceremony, but first we would like to share some of the science research that has been going on at Mineola High School. So it is my privilege to welcome our president of the Science National Honor Society, Ms. Colleen Talty, who will be speaking to you today on her research project that she conducted at Brookhaven National Laboratories on the composition of crystallization surfaces and its impact on protein crystallization. So I would like to now turn it over to Ms. Colleen Talty.
Hi, our project is studying the composition of crystallization surfaces and its impact on protein crystallography. Protein crystallization is a field of research that allows for the discovery of the molecular structure of a protein by crystallization of the sample. It is the most effective method for protein structure discovery. This process begins by manipulating a liquid protein to crystallize. This occurs under very specific conditions that are unique for each protein. It only takes one quality crystal to grow, to be harvested, and exposed to a light source to give off diffraction data. Diffraction data reads the electron densities given by the crystalline structure of the protein from that data. A 3D model of the protein is produced. Now, a majority of diseases are caused by abnormality in protein structure, including Tay-Sachs and muscular dystrophy. With knowing the structure of the abnormal protein, drugs that are compatible to the abnormal shape can be created. However, many proteins do not make it to this stage because the optimal environment for crystallization is unknown. Because of this, many proteins that cause incurable diseases are deemed uncrystallizable. For instance, when proteins are undergoing crystallization, scientists make sure to account for the temperature, the pH of the liquid sample, and the concentration of the buffer solution prior to experimentation, because each protein will crystallize best under their own specific conditions. However, one factor listed scarcely in the literature would be the surface that the proteins were mounted on while crystals were being formed. In other words, there was no guarantee that there was uniformity among the field in surface composition while crystallization was happening. This led us to a research question. What effect does the surface composition on which the protein is grown have on crystallization? Again, we tested this variable because many scientific papers that will list the conditions do not include the surface the proteins crystallized on. After further research, we saw that for the papers that did, the crystallization plates ranged from 6 different surfaces. Because of this wide range in surface material options, we saw importance in testing if this factor played a role in crystallization, and if so, to what extent. To test the effect of surface composition on crystallization, 2 test proteins, lysozyme and xylanase, were made into liquid samples and held at conditions optimal for that protein. The samples were then dispensed onto the 6 materials that we saw in the literature. This included Kapton, Mylar, COC, glass, polyethylene, and polypropylene. We set up our own crystallization plates because by 3D printing our own labware, we ensured that surface composition would be our only variable tested. We mounted the 6 materials to the custom plates and organized them into one central plate. 2 trials were conducted, and the plates were split into 2 so that 2 buffers were included in the experimentation to ensure that at least one of the buffers used would be compatible for both proteins. To dispense the proteins onto the 6 materials, the Echo 550 was used. This machine utilizes acoustic droplet ejection technology. This feature reduces contact and ensures that each droplet is of the same volume. In doing so, this machine negates human error that would be seen with standard pipetting. Now, crystals were looked at 3, 5, and 7 days following dispensation, and they were also scored each day. A scoring process was developed to measure the quality of the crystals. Crystals were given a score between 1 and 5 based on how well we think that they would react to a light source. Crystal area was also recorded using ImageJ software. The area and quality overall will indicate how well crystallization occurred. The area and score sheets were organized into an Excel file, and from that data, a heat map was created. This visual shows that, contrary to what is assumed in the field, there is no one optimal material for all proteins to crystallize. In fact, lysozyme crystallized best on glass, with COC as a close second, whereas xylanase crystallized best on polyethylene, followed by polypropylene. Now, we were able to see that our work does have a strong application to the field of crystallography. In our laboratory, our method was shared with a scientist who had 2 proteins deemed unsolvable because they could not crystallize. These proteins had been worked on for 2 years and no progress had been made. However, when our method was applied to the 2 proteins, it was clear that of the materials tested, the protein grew abundantly on COC and nothing else. These crystals were brought to the light source and the structures have been solved this summer. This method had also been shared with the scientists in Spain, and only with the application of our method were each of the proteins able to be crystallized. Legally, I am not allowed to disclose the name of the copper oxidase proteins, but it was only with our findings that the proteins are no longer considered unsolvable. Thank you.
Hi, my name is Colleen Talty, and I'm the president of the Science National Honor Society. I would like to introduce the rest of the executive members, starting with Vice President Anushka Patel, our Treasurer Samuel Levitan, our Recording Secretary Madeline Irish, and our Corresponding Secretary Carmen Lima. Thank you all so much for attending the virtual induction of the junior class. We understand that this year is unlike any other, but still the students tonight deserve to be recognized for their years of hard work and dedication to science. Before we begin the induction, we would like to thank the district, our superintendent, Dr. Michael Nagler, and the school board for the continuous support and encouragement in various STEM initiatives, as well as the science research program here at Mineola. We would also like to thank our principal, Dr. Whitney Smith, our assistant principals, Ms. Heather Dvorak, Dr. Lisa Downey, and Mrs. Jenny Fahey for their support and encouragement as well. At this time, I would like to invite Vice President Anushka Patel.
Tonight, we honor the academic achievement and excellence of these students in the field of science. To be accepted, these students had to achieve an overall GPA of greater than 90 and maintain an average GPA in their science classes of 90 or greater. In addition, they had to have taken at least one honors level science class before junior year and an advanced science class in their junior and senior year. This is quite an accomplishment of which they should be proud. At this time, I would like to invite Samuel Levitan.
And now I'll read the charter for the Science National Honor Society. Whereas the universal pursuit of knowledge and the common desire to share thoughts and the steadfast principle of discipline, integrity, and honor in all aspects of life flow true and sincere in this place of education, the Science National Honor Society Incorporated grants through this charter the privilege and ability to establish and maintain the Mineola High School Chapter 714 of the Science National Honor Society. At this time, I would like to invite Secretaries Madeline Irish and Carmen Lima to introduce the inductees of the Science National Honor Society.
We are proud to now introduce the inductees of the Science National Honor Society for the class of 2021. Grace Bang, Kristen Bennis, Kirsten Bennis, Veronica Carr, Wenny Chang, Isabella Gaglione, Yesenia Hanif, Megan Heckelman, Jibin James, Jessica Kessler, Joshua Kessler, Serena Koshi, Isabel Lopes, Matthew Manovitz, Hannah Mongayanu. I would now like to welcome our corresponding secretary, Carmen Lima, to introduce the remaining inductees.
Ksenia Maratov, Colleen Miller, Alexander Mora, Kira Mulrooney, Emma O'Sullivan, Jana Palumbo, Neha Parambi, Jillian Perino, Julia Perino, Isabella Polanco, Julia Rodriguez, Anna Victoria Serna, Caitlin Servinskis, Maya Simbulan, Renoy Thomas, and Ian Timoteo Franza. Congratulations on all of your achievements. And now for the closing remarks, President Colleen Talty.
Congratulations to the new members of the Science National Honor Society. We understand that the effort each and every one of you put into your academics should be acknowledged and celebrated, but despite the circumstances, you should all be beyond proud of what you have achieved. So thank you everyone for attending and have a good evening.
And that brings to an end our Science National Honor Society virtual induction ceremony. I would like to welcome all of the new inductees to the Science National Honor Society, Chapter 714, and thank everyone for joining us. Take care and be safe.